Welcome to qnawire.
All right, in part A, we are supposed to write the balanced chemical equations for the oxidation of Fe2 plus, and then they give us a list of things they want to oxidize by. You're supposed to use the reference equations that they give you in the problem. So we're trying to oxidize Fe2 plus to Fe3 plus. So we want to get Fe2 plus to Fe3 plus. And the first substance that they want us to do this with is S2O6. So that would be your second reaction that they give you there. So in this first one, this is the first one of part A. I'm just going to write out the reactants and the products first, and then we'll figure out the balance. So I have Fe2 plus, and then S2O6 2 minus, and in that reaction the other substances on the left side with the S2O6 2 minus are 4H pluses and 2 electrons, but I'm not going to worry about that because I'm going to cancel that out here. Since this reaction had 2 electrons and this one only had 1, this one's going to be multiplied by 2 to get the number of electrons to be the same. So that will be 2 Fe3 plus, and then on the right hand side for that S2O6 2 minus reaction we have 2 H2SO3s. So that's the reaction for the first one, and this reaction involved 2 electrons. This one, once I multiply by 2, involved 2 electrons. And that's going to be kind of important later, so I'm going to write that off to the side. All right, the second equation, I am oxidizing Fe2 plus using N2O. And if you look at the equations, again, the Fe equation as written only involves 1 electron, but our N2O involves 2. So I'm going to be multiplying this by 2 to get the same number of electrons. So that's 2 Fe2 plus N2O plus, and then that reaction also has 2H pluses on the left. We don't write the electrons because they're being canceled. And that yields 2 Fe3 plus N2 plus H2O. Again, I'm just basically copying what it says the reactants and products are from the reactions that we're adding together. And that again involved the transfer of 2 electrons. In the final equation, I am oxidizing my Fe2 plus with VO2 plus. That reaction only involves 1 electron, so I don't need to multiply my iron reaction by anything. They both involve 1 electron. So that's going to be plus VO2 plus 1 plus 2 hydrogen ions yields Fe3 plus VO2 plus and a water. And that involved the transfer of 1 electron. All right, so those are my balanced reactions for those three different reactions. In question B, we are asked to calculate delta G naught under standard conditions, so we are at 298 Kelvin, hence standard conditions. So the equation for delta G is delta G equals negative NFE, standard. So first we need to calculate our E cell for each one of these. And that's going to be they give us the reduction potentials there, and so remember E cell is equal to the reduction potential for the reduction reaction minus the potential for the oxidation reaction. So I'm just going to use the numbers up there in this first one. So the iron is the oxidation in each case, so it would be the S2O6 value minus the iron value. So for this first one, my my E is negative 0.17 volts. For this one, my E cell would be the value for E of the N2, so the negative 1.77 minus the value for the iron of the 0.77. And so the E cell for that one is going to be a negative 2.54 volts. And then my E cell for this final equation is, again, the E for the VO2 plus, which is 1, minus the 0.77, so that is a 0.23 volts. So now I'm going to come down here, and for each reaction I'm going to calculate G. So delta G is equal to negative, and N is the number of electrons. So for this first one, that was 2 moles of electrons that were transferred, times Faraday's constant, which is 96,485 coulombs per mole. And that would be like per mole of electrons, so that cancels there. Times the E for that, the E cell, so that was times a negative 0.17 volts. And a negative times a negative, I get a positive, and then coulombs times joules, I'm going to get, coulombs times volts, I'm going to get joules. So I get here 32805 joules, and I'm going to change that into kilojoules and round to 2 sig figs, significant figures, so that's 33 kilojoules. On question 2, reaction 2, delta G is going to be equal to negative, and again this is 2 moles of electrons for the second reaction, times my 96,485 coulombs per mole, times my volts, which is negative 2.54 volts, and that I'm going to get in 490,143 joules. Converted to kilojoules by divided by 1,000, rounded to significant figures, I get 490 kilojoules. Finally, for the third equation, delta G naught is equal to negative, and in this case there was only 1 electron, so 1 mole of electrons, times the 96,485 coulombs per mole, times the voltage on this guy, which is 0.23. So for this one, I get a negative 22,191 joules, which is equal to a negative 22 kilojoules. Finally, for part D, or C, sorry, I'm asked to calculate the equilibrium constant for each one of these. So the equation for the equilibrium constant, so we know that delta G is equal to negative RT natural log of K. If we solve that for K, the equilibrium constant, we get that K equals E to the negative delta G over RT. That's standard. So I'm just going to plug all those numbers in. I calculated my delta G's here. You do need to convert them. You need to go back to the original joule value here, the unrounded joule value in this equation for your delta G. Your R, the R that you should be using is 8.314, and that's joules per mole Kelvin, and then your temperature needs to be in Kelvin. So I'm going to plug in one of them here. So for the first reaction, K is equal to E to the negative, again I'm going back to this original value, so 32805 joules divided by R, which is 8.314, and that is joules per mole Kelvin, running out of space here, times the temperature, which is 298 Kelvin. And I plug all that in and I get that K equals, for this first one, 1.8 times 10 to the negative 6th. And you just plug the same things in, the same exact thing. For the other ones, the only thing that's going to change is this joules, the delta G value, which is going to change to these guys. So for the second one, when you plug that all in, you should get that K equals 1.2 times 10 to the negative 86. It's a very small K. And on the last one, K equals 7.8 times 10 to the third.